So you've got the sun. You've got the core of the sun. The core is fusing like furiously for a long time. Between 10 and 12 billion years is how long the sun will live on the main sequence. But eventually it's going to die. Eventually it's going to evolve off of the main sequence. So what does that mean? Well, what's going to happen is, right now we've got the sun, okay, and we've got the core, and the core is doing all this fusing, and the core is fusing and fusing and fusing, but over time it's shrinking. The core is shrinking a little bit smaller, and when it does, it causes the sun to expand a little bit, okay, and so that's the process that's happening. But eventually the core runs out of hydrogen and stops fusing. When it stops fusing, the core shrinks smaller and smaller and smaller, gets hotter and hotter and hotter. As it gets hotter and hotter and hotter, it starts heating up the mid layers of the sun, which start really pushing outwards, and the sun starts swelling up really, really big. Okay. When that happens, it's going to eventually swell up so big, it's no longer on the main sequence. When the sun swells up to the point it's no longer on the main sequence, then it's going to be, imagine we got the main sequence over here, it's going to swell up so it's no longer on the main sequence, so it's going to get bigger. The outer parts are going to get cooler. You're no longer producing heat on the interior. You're not making it hotter and more fusion, so the outside gets a little bit cooler, and it's going to get bigger and cooler, and it's going to be a subgiant. Okay. In the subgiant, you have a dead helium core. That core is not fusing anything. Surrounding it is compressed gas that when you heat the gas or you squeeze the gas, it heats up. When it heats up, it expands. When it expands, it pushes outwards here and causes the outer layers of the sun to really get pushed outwards. When they really get pushed outwards, these distended outer layers eventually get cooler simply because you're expanding a gas. Squeeze a gas gets hotter, expand a gas gets cooler. And so at that point, the sun is going to be this dead subgiant. No more nuclear fusion is happening in the core. Now, for a while, the sun stays here, okay, with the core gradually shrinking. We're back to Kelvin-Helmholtz contraction in the core. So the core gradually shrinks a little bit, gets hotter, okay, as it releases heat that allows it to shrink a little bit further, okay, and so the interior of the sun is maintained a little bit of stability right here, okay, shrinking, it's not really stable, but it's dying in a quasi-stable state, okay. Eventually, however, though, that heated layer of gas just above the core starts its own nuclear fusion because because the core is shrinking, so that layer is shrinking, so it gets higher and higher pressure and higher temperature, and when you get that higher temperature and the higher pressure, it starts fusing. Now you're not fusing the core, but you're fusing in a shell surrounding the core. That makes the layer right above that really hot. When it gets really hot, it really expands. The outer layers of the sun massively expand outwards, and so they start really expanding outwards, and when they do, they really cool off. And so what happens is the sun at this point, while it's fusing in that shell, really expands and becomes what we call a red giant. So the outer part gets really big, okay, and really cool, and becomes a red giant. Okay. The sun does this, and pretty much all the other stars do too. As they expand here, for really hot stars, then they tend to get cooler faster than they tend to get cooler faster than they get brighter. The sun tends to get brighter faster than it's cooling. At any rate, they end up in the upper right part of the HR diagram, and they are much more red than they used to be. And they are very large and very bright because they're very large, hence red giants. So when the sun expands to be a red giant, okay, it's first of all expands to be a subgiant because the core dies, and it starts shrinking, it heats up, okay, and then when you start fusing that shell, that causes it to expand to be a red giant. Okay, so in a red giant star, you have a core that's not fusing anything, but you have a shell of gas fusing hydrogen into helium. Now, what happens to all the helium? Well, it's heavier than hydrogen, so it actually sinks in the core, makes the core actually bigger. Okay. The Hipparcos satellite shows HR diagram here, and you've got most stars are along the main sequence here. Okay, we got some white dwarfs down here, and then you have all these giant stars up here. And so all those giant stars up here, you know, and then we have the supergiants way at the top. We'll worry about them later. But those giant stars are basically dead and dying stars. Kind of a last gasp of them dying here is fusion not in the core but in the shell. So they're, I guess you'd say they're kind of almost on life support at that point. How big is a red giant star? Well, when the sun first swells up to be a red giant star, it has a diameter of about an AU. Now remember, an AU is the distance from the Earth to the sun. So that means that the edge of the sun will be halfway between where the sun currently is and where Earth is. Well, gosh, that's not very good for Mercury, because Mercury orbits the sun at about 0.3 something AU, about 0.39 AU. So that's much less than 0.5. And so, you know, you would say, oh, wow, that would suggest that the sun ate Mercury. These red giants tend to be very bright. So you see a lot of them in the sky. The star Arcturus, which we saw early in the semester, that is a red giant star. Okay, so Arcturus and the sun by comparison to give you an idea of size. So the view from Earth when the sun swells up to be a red giant. And it's not going to be nice, because that means the sun would actually swell up so big in the sky that even though the surface of the sun is a lot less than it currently is, the size of the sun is going to be so big, the surface area is so big, that the total brightness is going to be higher. So that means that Earth would basically heat up to the point that you would actually boil away not just the oceans, but you would strip the Earth of its atmosphere. It'd be too hot for Earth to even maintain an atmosphere. In fact, the surface of the Earth would be so hot that the rocks themselves would be in danger of melting. So we're almost at the point of melting the surface of the planet. So really, really hot, really miserable weather. The outer part of the sun will be stretching out so far from the center of the sun that it's real easy to push things away. So you have these streamers, probably this artist's impression is probably correct. You have streamers of coronal gas and other sort of stuff pushing away from the sun.